I want you to imagine for a second that you are building this massive, intricate machine. You spent weeks wiring it together, writing thousands of lines of instruction.
Right, to govern every single gear and pulley.
Exactly, every conceivable scenario. And you finally hit the power button, fully expecting this whole apparatus to just hum to life. But instead, the gears lock up.
The engine stalls.
Yeah, the entire system just grinds to a devastating halt. And when you grab your flashlight and dig down into the architecture to find the problem, you realize you actually didn't make a structural error.
It wasn't a backward part or a loose screw?
No, the machine didn't break because a part was installed backward. It broke because of empty air, a completely blank space where the machine expected something to be. Welcome to the deep dive.
It's an incredibly common trap in software development. We spend so much time building the architecture to handle complex data. We completely forget to teach the system what to do when it encounters the void.
Right, and that void is the focal point of our mission today. We are looking at a very specific, real-world coding journal entry. It's titled Notes on Haskell Programming, Part 148.
Yeah, written by a developer named Ang.
Exactly. Published on May 29, 2026.
It's a really great case study because it isolates this highly specific bug and then walks us through a deeply elegant one-character fix.
Yeah, we are going to explore how a tiny, invisible assumption embedded in a code base can just completely paralyze a system. Now, we will be getting into the weeds of a specific programming library called Megaparsec.
Right, which sounds intimidating.
It does, but listen, for those of you listening without a computer science background, do not worry. You don't need to know any Haskell to follow the logic here. This is fundamentally a story about how machines interpret instructions differently than human beings do.
Yeah, if you look closely at the core problem Ang was trying to solve, it really just comes down to that friction between human intuition and machine literalism.
Let's set the stage with the bug itself. Ang was working on a parser. In this context, Ang was feeding this software a bunch of different digital novels to automatically extract the metadata.
The title, author, publication date, genre.
Right, all that front matter you see before Chapter 1.
It's basically a task of organizing unstructured text into a structured database. You're telling the software to look for specific labels, read the text associated with those labels, and then file it away.
But the parser suddenly started failing. Ang would run a batch of novels through the system, and it would just choke. It completely refused to process the metadata on certain files.
Which is incredibly frustrating.
Oh, absolutely. So after digging through the trace, Ang tracked the failure back to the specific chunk of code responsible for reading the individual metadata fields. And the flaw was an implicit demand written into the code.
The demand that the value of every single metadata field was absolutely required to exist.
Right. The code was written under the assumption of presence. If it looked for a publisher, there had to be a publisher listed. It completely lacked the capacity to process absence.
Yeah, to process nothing.
To visualize how ridiculous this looks in practice, think about dealing with a rigid government bureaucrat processing a physical form at the DMV.
Oh, everyone's favorite scenario.
Right. So you walk up to the glass, and the bureaucrat hands you a paper application that asks for your first name, middle name, and last name. Now, let's say you don't have a middle name. You just leave that specific box blank and hand the clipboard back.
Sure.
A human being looks at that blank space, uses basic context clues, and thinks, okay, this person doesn't have a middle name. I'll just move on to the last name.
Because we process the absence of information as its own kind of information. The blank space tells us something useful.
Exactly. But our machine bureaucrat doesn't have human intuition. You slide the form across the desk with a blank middle name box. The bureaucrat looks at the empty rectangle, hits a giant red alarm button, throws the entire form in the shredder, and shuts down the DMV.
Just total chaos.
Complete chaos. Because their boss gave them a manual that explicitly stated every single box on this form must contain ink. If a box lacks ink, the entire reality of the form is rendered invalid and the process cannot continue.
And the machine acts this way because, well, computers only execute explicit instructions. They don't fill in those logical gaps for you.
Right. They just do exactly what they're told.
Exactly. When a developer writes a command to, capture the text following a label, the computer expects text to actually be there.
Makes sense.
To a parser, nothing isn't just empty space. It's an unexpected state that completely violates its programmed universe.
So if the whole system crashed because it demanded ink on the paper, the fix has to involve fundamentally changing that demand, right?
Right.
Let's look at exactly how Ang rewrote the rulebook for our screaming bureaucrat.
Yeah, the structural change Ang made to the codebase is remarkably subtle.
I'm looking at the code diff Ang provided, the before and after snapshot of the code base. The old line of code, the one triggering the failure, relied on a function called takewhile1p.
Right.
Ang literally just deleted that function and replaced it with a very similar one called takewhileP.
The entire fix boils down to the removal of a single digit, the number 1.
I have to admit, when I first read through the journal notes, this specific fix really tripped me up. I understood the bug. The system couldn't handle empty fields, but I didn't intuitively understand the solution.
It's not super obvious at a glance.
Right. How does removing a single digit from a function name stop the system from panicking over missing data? Let's unpack this.
Okay, so to understand the mechanics of the fix, we really have to look at how a parser physically reads a document. It doesn't read a whole page at once like you or I do.
How does it do it?
It operates more like a cursor blinking on the screen, just moving left to right, evaluating one individual character at a time.
Like someone reading a book through a tiny pinhole, seeing only one letter per second.
That is a great way to picture it. Now, Ang outlines the sequence of arguments this specific parser uses when it hits a line of metadata. First, it looks for a label.
So the cursor scans along until it finds the word translator, followed by a colon.
Yes. Next, the parser is instructed to look for a string of text, and this is where the evaluation gets highly specific.
Okay.
The parser checks the characters it's reading against a mathematical condition, which we call a predicate. In this case, the predicate is checking whether the character it is currently looking at is a new line.
Let me pause you there, because that term might be confusing. When we hit enter on a keyboard, we just see the text drop down to the next line, but the computer actually writes a hidden character there, right?
Correct. In programming, that hidden character is often represented visually as a backslash followed by an N. \n. It's a literal character that tells the machine to move the cursor down.
Okay, so the parser finds the label translator. Then it starts looking at the characters immediately following the colon, and it's checking each one to make sure it's not that invisible new line character.
And here is where the old function, takewhile1p, caused the catastrophic failure. That number 1 in the function name is a strict mathematical threshold.
So it's a requirement.
Exactly. It instructs the parser, you must find at least one character that satisfies the condition before you hit the new line.
So if the book actually has a translator, the cursor reads, translator, Smith. It looks at the S. Is it a new line? No, that's one character. The threshold is met. It can read the rest of the name, hit the new line at the end, and everything is fine.
But consider what happens when Ang feeds the parser a self-published novel that does not have a translator. The text file literally just says translator and then immediately drops to the next line.
So the label is there, but the field is blank.
Yes. The cursor finds the label. It moves to the next space to begin evaluating characters against its condition. But because the field is blank, the very first character the cursor encounters is that invisible new line character.
Oh, wow, I see the collision now. The takewhile1p function demands at least one valid character, but on the very first try, it hits the new line. It grabbed 0 valid characters.
The threshold was not met. The rule was broken, and the parser has no instructions for what to do when it grabs 0 characters, so it throws a fatal error and the entire process dies.
Our bureaucrat looked at the empty box, found no ink, and hit the red alarm. So by changing the function to takewhileP, dropping the 1, Ang is shifting that mathematical threshold.
Right. The new function, takewhileP, allows for 0 or more characters to match the condition.
It changes the baseline expectation. Instead of demanding, you must give me at least one character, it relaxes the rule to give me whatever you have, even if it is absolutely nothing.
Mechanically, the cursor moves past the label translator. It encounters the new line character immediately. But because the new threshold accepts 0 characters, the parser simply logs that it found nothing, satisfies its own rule, and calmly moves on to the next line of metadata.
The bureaucrat is given a new manual that says, if the box is blank, just skip it. And the line at the DMV starts moving again. The forms get processed.
It really is an elegant shift in logic.
It really is. But, as we look closer at these two functions, takewhile1p and takewhileMP, there is a naming convention trap here that Ang explicitly warns the reader about in the journal entry.
Yeah, it's a cognitive trap that trips up a lot of developers when they are first learning these parsing libraries.
I completely fell right into it while reading the source material. We just spent all this time talking about how the function checks characters against a condition we define as a predicate.
Right.
So when I look at the function name takewhileOP, My brain immediately assumes the uppercase P stands for predicate. The function takes characters while the predicate is met. It just seems totally intuitive.
It's a very logical assumption. I mean, it makes perfect sense. But ang stops the reader specifically to correct it. The P in these function names does not mean predicate.
Wait, really?
No, it actually stands for parser.
And my immediate thought reading that was, why is Ang going out of their way to clarify this? If the code works, why does it matter to the programmer whether the P stands for predicate or parser?
It matters deeply because understanding the difference between those two concepts is really the key to understanding why Ang chose to use the Megaparsec library in the first place. The P functions in this library operate on a fundamentally different level than a standard predicate.
Okay, let's explore that difference then. How does a parser function operate differently than a basic predicate function?
Well, a standard predicate is essentially a blind binary test. True or false, yes or no. Is this specific character I am looking at right now a new line? Yes or no. That is the absolute limit of its awareness.
If we bring back our DNV bureaucrat, a standard predicate is a bureaucrat wearing horse blinders, looking through a paper towel tube.
Oh, exactly.
They can only see a single 1-inch square of the form at a time. They have no idea what page they're on or even what form they're reading. They just look at the box and yell, ink, or no ink.
That is a perfect visualization because if a standard predicate encounters an error, it simply fails. It throws a generic exception. And as a developer, you receive an error message that says something incredibly unhelpful, like syntax error.
Which is an absolute nightmare when you're trying to debug a complex system. You have a massive file with thousands of lines of text, and the computer essentially just shrugs and says, something is broken somewhere.
It's the worst, but the P functions in Megaparsec, the ones Ang is utilizing here, they're different because they possess an internal awareness of the parser state.
Awareness of the parser state. What does that actually mean for the software as it reads the document?
It means the function isn't just blindly evaluating true or false. It is actively maintaining a continuous map of its own traversal through the data.
Oh, wow.
Yeah, it tracks the exact line number it is currently reading. It tracks the exact column number. It tracks the specific sequence of tokens it has consumed to get to its current position.
So our bureaucrat takes the paper towel tube off. They don't just see a single box anymore. They have a detailed ledger. They know they're on page 4, section B, line 12.
Exactly. They have situational awareness. And the benefit of this state awareness becomes incredibly clear the moment the system encounters an error.
Because it knows context.
Right. When a Megaparsec P function hits an unexpected state like finding a blank space where it expected a character, it doesn't just throw a generic panic and crash.
Because it knows exactly where it is.
It pauses, pulls its internal coordinates, and generates a highly specific, laser-focused error message. Instead of a vague syntax error, it tells the developer, look exactly at line 4, column 12. I was expecting a character, but I encountered a new line.
It hands you the precise geographical coordinates of the crash site. And, looking back at the timeline of Ang's bug, this underlying architecture is likely the exact reason Ang was able to isolate the problem so quickly in the first place.
Oh, absolutely.
The parser choked on a blank metadata field, but it didn't fail silently. The P function's state awareness generated the map that led Ang directly to the faulty take-well1p instruction, bringing the whole debugging journey full circle.
It really demonstrates how crucial your choice of tools is when building complex systems. A library that fails gracefully and provides locational context empowers the developer to actually understand the failure and rewrite the logic.
We started this deep dive looking at a machine that crashed because it encountered empty space. We traced the bug to a rigid mathematical threshold, the demand for at least one character, and explored the mechanics of the fix. Swapping take-while1p for take-while-p changed the system's baseline expectation from demanding presence to gracefully accepting absence.
And we decoded the naming convention, revealing how state-aware parser functions maintain the necessary context to make debugging possible.
It's a really great technical journey, but the broader concept here extends well beyond Haskell code or software development. I think Ang's journal entry forces us to look at the foundational assumptions we build into any kind of structured system.
For sure. Every system, whether it is a digital database, a corporate policy, or a legal framework, is built on a bedrock of implicit expectations.
We design our systems for the data we expect to receive. We expect everyone to have a middle name. We expect every self-published novel to have a translator listed. We expect the people interacting with our systems to fit into the neatly labeled boxes we have drawn for them.
But the real world is messy. It's unstructured. It is full of blank spaces and missing variables. And when a system is entirely rigid, when it demands a one-to-one presence of information for every rule it has written, it becomes incredibly fragile.
It's a structural vulnerability, which leaves you with an interesting angle to consider the next time you interact with a frustrating piece of technology or a rigid bureaucracy. Think about the legacy databases running our financial systems, or the complex AI models trying to interpret human behavior.
Right.
How often do these massive, sophisticated architectures break down, not because the data they have is wrong, but because they simply lack the capacity to handle the absence of information? We spend so much energy teaching our machines how to analyze and organize everything, but Eng's journal entry is a great reminder that true resilience requires teaching a system how to understand nothing. Thanks for joining us on this deep dive.